Okay, so today is our 29th lecture. So yesterday we have seen the applications of Navier-Stokes equations, and we tried to see two particular cases of cold flow and plain Poiseuille flow, but both the cases were actually involving the Cartesian coordinate system. Okay, now we will try to consider some of the cases where we have to go for the cylindrical coordinate system. So in case of cylindrical coordinate system, the first case which we will be studying, that is called as Hagen-Poiseuille flow. Okay, so basically in this situation, what we have is we have a cylindrical pipe, and in this cylindrical pipe we are considering that flow of fluid is happening from left to right. Okay, so whenever we see that flow of fluid happens from left to right inside a pipe, then we find that there is some portion near the inlet of the pipe where actually flow velocity is not independent of the length of the pipe. Okay, that depends upon length of the pipe, but we will consider over here only the region within the pipe where flow velocity is independent of the z direction. Okay, so let me explain to you what I am trying to say over here. So whenever flow will be entering into the pipe, you will be finding that outside the pipe fluid is having uniform velocity. Okay, because it is not having, say, any free surface, any solid surface which is bounded from the top or bottom. Okay, so that's why outside the pipe it will be having nothing but the velocity which will be same everywhere. Okay, but whenever this flow will be entering into the pipe, in the top portion it will be experiencing a solid wall, at the bottom also it will be experiencing a solid wall, or if it is a pipe, then for the complete circumference it will be experiencing some solid wall. Okay, so because of that, immediately this particular vector which is looking like so big, it will become a point at the solid surface. Okay, and as this vector has become point, because of the viscosity of the fluid, it will also try to slow down the other components of the velocity which are just adjacent to it. So adjacent to it, I will be finding that velocity is not very high, but it has a slowed down and become this much small. Okay, and then after some portion I will get a region where velocity will actually become equal to that of free stream velocity. Okay, so the region in which this gradient of velocity is existing, we will be calling that region as nothing but the boundary layer. Okay, so like in case of flat plate, what was happening, the portion up to which this gradient of velocity was existing, that we were calling boundary layer, and away from that we were calling as nothing but the region outside the boundary layer where velocity gradient was equal to 0. Okay, so almost similar kind of situation will be existing over here, but in this case there are some key differences. Okay, so here what will be happening, say this boundary layer is growing with the length. We know that boundary layer grows with the length. It will keep on growing, it will keep on growing, but ultimately these layers will be actually joining each other, which are forming from both the sides, and ultimately at the center line these will be meeting. Okay, is this one clear? So if you have to plot velocity profile at any location over here, so at this location you will be finding that this is the zone where gradient of velocity is existing, and then in between almost it is flat. Fine, is this one clear?
So how did we make that consider the shape?
How did we make that?
So how did you consider like
This particular shape.
yeah.
So this shape, what I am trying to say over here is the portion where gradient of velocity is existing. If I join locus of that portion, that will be giving me the boundary layer.
All the points where the gradient is
Existing. So extreme point of this velocity profile up to which gradient is existing. After this point it is becoming
constant.
so that locus of all that points we are calling as boundary layer. Okay. So now what I am trying to say over here, the key difference which we will be finding over here, you can see that this was the free stream velocity. If I consider that I am having actually steady flow, Okay, so in case of steady flow, there should not be any mass holding within the system. So whatever the mass is entering at any cross section, same should be mass at each and every cross section. Okay, so in order to keep the mass same, you will be finding that this center portion of the velocity is actually increasing. It is going even larger than the free stream velocity. So is this point clear? Okay, this is very important point, that this is my free stream velocity, and this particular zone is having velocity which has become even greater than the free stream velocity. Why it has become greater than the free stream velocity? Because I have to keep average velocity same everywhere. Then only my mass flow rate will be same everywhere. So in order to keep the average velocity same, because in this portion velocity has gone below the average velocity, so in this particular portion I have to increase velocity above the average velocity. Is this one clear? So this type of velocity profile whenever I will be getting, so this zone I will be calling as nothing but the, so it will be happening like this, and after this point I will be experiencing that velocity profile will become, it will take some shape. What shape it will take, that mathematically we will derive, but after this point, if I keep on drawing velocity profile at any section, everywhere this shape and this value of velocity profile will remain the same. Is this one clear? Okay, all are clear with this idea? So what we do, this particular zone we call as nothing but the entrance region. This is called as entrance region, and this particular zone from where the velocity profile has become constant and it is not changing along the length of the pipe, that is called as fully developed region. This is called as fully developed region. Okay, basically I will once again come back to this particular topic later, when I will be specifically talking about the internal flows through the conduits. But at the moment, my only interest is I want to show you the application of Navier-Stokes equation in cylindrical coordinate system, and particularly whenever I will be showing you that application, I want to only focus on the fully developed region. I will not refer to entrance region. That's why I have just introduced you this concept at the moment, that what is the meaning of fully developed region. But ultimately later on again I will take this topic in more detail. Okay, is this point clear? So it means that when I am referring to the Hagen-Poiseuille flow, I am referring to only this portion of pipe which is having fully developed velocity profile. Is this one clear? So I am not referring to actually the developing region. Okay, so let me now draw the fully developed region over here. Say this is the zone which is showing the fully developed region. Now of course this is nothing but a cylindrical container. So though conduit, though I can also solve this using the Cartesian coordinate system, but then analysis will become more complex. Okay, because everywhere we have to consider the angles cos theta, sin theta, then only we will be able to find the values of velocity. So geometric transformations are to be used. So better way is, if I consider a coordinate system which is aligned with the flow only, then I will be easily able to find out the solution. Okay, so that is what I will be doing now. So now I will fix the coordinate system. So say this is my location Z, this is my coordinate along direction R, and one coordinate I will be having along direction theta. So it means for this system I have my coordinate system as Z, R and theta. Is this point clear? So my coordinates are nothing but R, theta and Z. Okay. So if you see now in this fully developed region, when I mentioned the fully developed region, I will be experiencing that after this point there is no change in the velocity. As after this point there is no change in the velocity, so I will be experiencing that in theta direction also there is no change. Okay, so it means that for this type of symmetric situation in the fully developed flow, my variation along theta direction will be nearly equal to 0. Is this point clear? That is the reason I will be also finding that velocity along theta direction is also nearly equal to 0. Is this point clear? Now, another extreme of this situation is that you can see all the velocity vectors are oriented towards the z direction. So it means that majorly the flow is in which direction? Z direction only. Okay, you cannot see any velocity vector which is pointing in the vertical direction. So it means that if no velocity vector is pointing in the vertical direction, I have a pure laminar flow situation. So of course laminar flow also I will discuss with you later, but at present you have to only remember that whenever I am referring to the laminar flow, I am considering that all the layers of the fluid are moving just parallel to the z-axis. There is no disturbances between the layers. Okay, so by considering this assumption, I can say that if there is no disturbance, all the layers are moving parallel to the z direction, I can say v of v of r will also be approaching to 0. Is this point clear? Please, I am just explaining by words. Please note down these assumptions. You have to write down these in the exam. Okay. So, one is del by del theta is nearly equal to 0, v theta is nearly equal to 0, and third is Vr is nearly equal to 0. Okay. Now, what we will be doing, if I consider that there is no variation along theta direction, okay, so it means that I have to only solve the equations in Rz plane. Is this point clear? So only I have to solve the equations in Rz plane. So it means I have got a two-dimensional system, and in this two-dimensional system I am only interested in the Rz plane. So when I am doing so, my simulation domain will become, my this analytical system domain which I am solving over here, that will become only this portion. So this dashed blue color line is showing the control volume which I am considering at the moment. Okay. So this is the control volume which I am considering, because whatever solution I will be getting for this control volume, same will be applicable for the complete 360-degree rotation of this particular plane. Is this point clear? Because this center line is nothing but forming a axis of symmetry. This is becoming axis of symmetry. About this center line, at each planar location I have the same profile. So that's why I am only solving a plane, and this plane I will be rotating about this axis through an angle of 360 degree in order to get the full solution. Okay, so I am taking over here the advantage of physical symmetry of the situation about its axis. Okay, so if situation is not symmetric over here, say if you say that your velocity profile because of any reason is becoming something like this, then you cannot apply this axisymmetric formulation. Okay, in that case what you have to do? You have to do the complete three-dimensional analysis of this system. Is this point clear? So the physical problem which we have considered in our hand, that physical problem is actually giving us a situation which is basically symmetric about the center line axis. So that's why I am considering it as only a two-dimensional system which we will be solving in Rz plane. Is this point clear? Otherwise, if situation is not symmetric, then we have to solve the complete three-dimensional system of equations. All are clear with this?
We are considering the plane, so we're considering only above the center line wala part.
Yes. Why I am not considering the bottom plane? Because what I am trying to do over here, this symmetry is about central axis. So if I consider only half of a plane, and if I obtain solution for half of the plane and then rotate it by 360 degree, then ultimately my complete situation is coming out. Okay. If in place of this, you refer to plane Poiseuille flow. So in plane Poiseuille flow, I don't have symmetry about central axis, but I have planar symmetry. I have two plates, and these two plates are parallel up to infinite length in the third dimension. So as these plates were infinite in the third dimension, so what I can say that if I consider a two-dimensional plane here, okay, from starting from top plate to bottom plate, whatever the solution I will be finding at this location, same solution I will be finding here, same solution I will be finding here. So that is called as planar symmetry. This is called as axis symmetry. Okay, this point is clear. So in case of plane Poiseuille flow, we have taken the advantage of planar symmetry. Here we are taking the advantage of axis symmetry. Is this point clear? What is the difference between the two? Okay, so now it is very clear to us that we have to only solve the system of equations in RZ system. So can you tell me what will be the continuity equation? 1 by R del y del R RVR plus theta term I will not consider because I am only talking about the RZ system, del by del Z of Vz equal to 0. Number 1. Okay. Number 2, we have to solve the R momentum equation. So R momentum equation will be rho times Vr into del Vr by del R plus Vz into del Vz by del Vr by Vz equal to minus del P by del R plus mu times 1 by R del by del R into 1 by R del by del R of RVR plus del square Vr by del Z square. So this is my R momentum equation, and in this equation I have removed all the theta terms. Point is clear? Then third I have to write down the Z momentum equation. So Z momentum equation will be rho times Vr into del Vz by del R plus Vz into del Vz by del Z minus del P by del Z plus mu times 1 by R into del by del R of R del Vz by del Z plus del square Vz by del Z square. So this is your equation in, these are your equations basically. Okay. Is it clear up to this point? Now we have to consider that what are the terms which are relevant in this system and what are the terms which are not relevant. Okay. So very simple. First go to continuity equation. From continuity equation we will get one very important conclusion. What is the conclusion? The point is, if you see the continuity equation, I told you that we are considering the fully developed region, and I mentioned the definition of fully developed region, that whatever the velocity profile I have got, after this point this velocity profile is not actually changing with Z. Or in other words, I have also told you that my flow is purely parallel to the z-axis. So as it is purely parallel to the z-axis, I will not be having any r component of velocity. So Vr is nearly equal to 0 over here. So as Vr is nearly equal to 0, so I can refer this first term to be 0. Okay, so if this first term is 0, it means there is no radial component of velocity, then ultimately from equation number 1, simply I am getting that del V z y del z is equal to 0. This I am getting from the continuity equation. It means for fully developed flow, del V z by del z is equal to 0. So it means the z component of the velocity in case of fully developed flow will not depend upon the length of the pipe. It will be independent. So it means that each and every location along the length of the pipe, once flow has become fully developed, everywhere you will be having same velocity profile. Is this point clear? Okay. Now the meaning is very clear, as I have just now told you that Vz is not a function of z. If Vz is not a function of z, we are only dealing with the r and z system. So Vz has to be a function of r only. Is this one clear? Vz has to be a sole function of r only. That is what is clear from the physical situation which I have drawn. So you can see in this direction my r is varying. So Vz value is varying around the r even in fully developed region. Point is clear? So whatever we are mathematically doing, we have some physical understanding behind that. Okay. So nothing we are solving equations. Every equation is having some physical meaning. Please try to consider this analogy, because if you are not able to make this analogy, then what will be happening if I give you some other unknown situation in the exam, then you will not be able to do that. So you should be able to make analogy and then consider which term you have to remove. Okay, so Vz has become only a function of r. Okay. Now what next? Let's go to r equation, r momentum equation. So Vr is 0, this term is 0, del Vr by del z has also become 0. This whole term is involving r, Vr. So this whole term will become 0. What you are left with? From equation number 2, one very important conclusion. Minus del P by del R is equal to 0. It means P is not function of R. It means P is a sole function of . So one important conclusion we have got, that whether you take pressure measurement at this point, at this point, at this point, everywhere pressure measurement will be same. But along the z direction, if you consider pressure at this point and at this point, then pressure will be different. Okay, along the z direction pressure will vary, and along the r direction it is not varying. Clear? Why it is not varying along the r direction? Can someone relate it from the concept of a streamline? So when we have derived the equation, Bernoulli equation for a streamline, okay, at that time we have only considered the component of the momentum equation which was parallel to the streamline. If I consider a component of the momentum equation which is normal to the streamline, then I will be finding that the pressure change across a curved streamline is nothing but equal to centripetal acceleration. Okay, but if you have a straight streamline, then you will be finding for a straight streamline the radius of curvature will be infinite, so centripetal acceleration will be 0. So that's why along a straight streamline pressure does not change. Okay, let me quickly show you that. So if you consider a straight streamline like this, I am not able to draw straight. Okay, so this is a straight streamline, and one is, say this is a curved streamline, something like this. So ultimately the point is, if you try to consider this as the normal direction, and in normal direction if you solve your momentum equation, you will be finding that del P by del N, pressure gradient in normal direction, will be proportional to V square by R, where R is nothing but, if I fit circle of this streamline at some large distance, then whatever the radius of this is, radius of curvature is there, that is nothing but R of this streamline. Okay, so it means as I move in normal direction across a curved streamline, the pressure will keep on increasing, and it's a function of V square by R. But if I consider a straight streamline, for a straight streamline R will be infinite size. If R is infinite size, then this V square by infinity will be becoming equal to 0, and pressure in the normal direction will not be different. So it means here and here pressure will be same. In this case, here pressure will be more, here pressure will be less. Is this one clear? So that's why, though this we are getting from Navier-Stokes equation, but ultimately we can also relate it from the concept of streamline. No, when we solve momentum equation, we have only, while deriving Bernoulli equation, we have only taken the parallel component. But if I take the normal component, then this is the important result which I will be getting. Okay. So this is one master tool for you, that wherever you find streamlines are straight, in this case what will be happening? Velocity is straight, it means streamlines will also be straight. So wherever you find streamlines are straight, you can say at every point pressure is same. Wherever you are finding streamlines are curved, it means pressure is difference. On convex side pressure will be more, on concave side pressure will be less. Fine. So this is just another interpretation I am giving. I need not to utilize the concept of streamline over here, but this is the additional thing which I have introduced to you. Okay. Is this one clear? So minus del P by del R has become now equal to 0. P is not function of R, P is only a function of Z. So my second equation is done. Now let's go back to the third equation. From third equation, what I will be getting? VR is 0. Del V Z by del Z is also 0 from continuity equation. Okay. Then in the right hand side, if del V Z by del Z is 0, del square V Z by del Z square will be 0. But Vz is a function of R. Sorry, I have written one term wrong over here. This should be del Vz by del R. Please make this correction. Clear? So now Vz is a function of R. So that's why this entire term will be non-zero. And this term also, we don't have any information about this. We only have information about this, that pressure is a function of Z. So that's why I will be having existence of del P by del Z also. Okay. But this del P by del Z, now I can write dP by dZ, and velocity is a strong single function of R only. So dou by dou R I can write as d by dr. Okay. So ultimately my equation number 3 will be becoming then mu by R, one R I have taken outside, into d by dr of R dVz by dr equal to, this was minus, so that has become equal to dP by dz. So all are fine up to this point. This is something which we are getting from equation number 3. Okay. One of you please start writing your name on a paper and then circulate it. Name and roll number. Please don't mark proxy, I have already counted. Otherwise, I will mark all absent. Okay, so. So now, this is my equation. Clear? Now what we have to do? From the previous formulation which we have done yesterday for plane Poiseuille flow, I can say mathematically this will exist only if this is equal to a constant. Now flow is happening from left to right. So as Z is increasing, pressure should decrease. So that's why it should have a negative sign. Okay. So now what I have to do to find out the solution? I have to integrate. So what I will do first, I will take mu by r to the other side. So d by dr of r dvz by dr equal to 1 by mu into dp by dzr. Fine. So if I take the first integration, then this d by dr will vanish. I will be having on the left hand side r dvz by dr equal to 1 by mu, rather 1 by 2 mu in dp by dz into r square plus c1. Is this point clear? Now I have this r in the multiplication, so I must divide it before integrating. So I will be getting dvz by dr equal to 1 by 2 mu into dp by dz into r plus c1 by r. Okay, and if I again do integration, then I will be getting vz as function of r equal to 1 by 2 mu into, sorry, 1 by, it will be becoming now 4 mu dp by dz r square plus 1 by r integration will be becoming c1 ln of r plus c2. Fine. So now what is our interest? Now our interest is to calculate the values of c1 and c2. So very simple assumption, though from physical nature of the solution which I have explained, you can say two boundary condition, because now I am only solving this planar system. So first is at this solid wall I will be having Vz equal to 0. So say if this is nothing but my capital R, radius of the pipe. Okay, so capital R is radius of the pipe, internal radius of the pipe. So at R equal to, please consider this point also, when I am solving, I am only solving the fluid domain. So if say pipe is having some thickness, that is not part of my control volume. So I am referring to the internal radius of the pipe. Is this point clear? So at internal radius of the pipe, my Vz will be equal to 0. Fine. All are clear with this boundary condition? What will be second boundary condition? Second boundary condition, if I look at this particular velocity profile, I know at center it will be maximum. So I must have gradient of that velocity with r, means del Vz by del r equal to 0 at the center line. But this is coming from my physical interpretation. Okay, let's say I don't know whether at center I have gradient 0 or not. So in that case, what I will do, one assumption I can make, that I am not very sure whether del Vz by del r is equal to 0 or not, but I am very sure that at the center value of Vz is finite. All are clear with this idea? It has some finite value. Okay, so two boundary conditions which I can impose. One is very clear, no slip boundary condition, which will be giving me at r equal to capital R, my value of Vz is equal to 0. Okay, and second boundary condition which I can consider at r equal to 0, at center line, my Vz is having some finite value. Okay.
Sir, why can't we take the boundary condition of r equal to minus r over here?
Because I have taken my domain, I have taken only this much domain, which is starting from r equal to 0 only. Fine. I am not solving the complete plane, half of the plane only I am solving over here. What I will be doing now, please tell me. So Vz is equal to 0. So 0 equal to 1 by 4 mu into dp by dz capital R square plus C1 capital C1 ln capital R plus C2. Equation number 4. Equation number 5. Vz is finite. So finite is equal to 0. When you will be putting R equal to 0, this is 0 plus C1 ln 0 plus C2. Okay. Now from mathematics, natural log of 0 is undefined, but my value of Vz is finite. So this ln of 0 undefined, I can make only 0 if my constant C1 is 0. So it means from equation number 5, I can clearly say that C1 has to be 0. So if C1 is 0, then from equation number 4, I can calculate that C2 will become minus 1 by 4 mu into dp by dz R square. All are clear with this idea? Okay. So now I can substitute the value Vz as function of R is nothing but equal to 1 by 4 mu into dp by dz R square minus 1 by 4 mu into dp by dz capital R square. Okay. So ultimately my Vz of R equal to 1 by 4 mu. I will be putting minus sign with dp by dz because gradient will be negative for a physical scenario. So inside I will be getting capital R square minus small r square. Okay. Now from this equation, if I substitute small r equal to 0, then I am able to get the maximum value of the velocity. So I can say that at r equal to 0, Vz will be equal to Vz max, and that maximum value will be 1 by 4 mu into minus dp by dz capital R square. If this is the situation, then I can write Vz as nothing but Vz max times 1 minus small r square by capital R square. Okay. So from this point, one clear idea we have got that velocity profile is parabolic, and in 3D it will be a parabolite. Okay. So it means that the curve I have drawn is almost mimicking a parabola. Okay. What about wall shear stress? This is my wall. This is which plane? In normal direction, R plane, and direction I have to consider as Z. So I have to calculate tau R Z. Okay. So tau wall will be nothing but tau RZ at what point? R equal to capital R. So what it will be? Mu times del Vz by del R at R equal to R, because I am not writing the other portion, that will be ultimately 0 because VR is 0 only. Okay. So tau wall has become mu times Vz max into what is del Vz by del R? 0 minus 2r by r square. When I will be substituting small r equal to capital R, then I will be getting tau wall as mu minus 2 mu Vz max by capital R. So this is my wall shear stress. Okay. Now what about average velocity? V average. So area into V average must be equal to integral of Vz into dA, which is integral of Vz into 2 pi r for complete pipe, 2 pi r dr. So this area on the left hand side will be becoming capital pi capital R square into V average equal to Vz max times 1 minus R square by R square into 2 pi R dr. Please tell me fast what we will be getting. Do the integration. Integral from 0 to R. Now this integral will be from 0 to R. Okay. So it will be R minus R power 4 divided by 4 R square. So V average will be, pi will be cancelling out, 2 Vz max Oh, sorry, R square by, yes, this R will be multiplied. Yeah, R square by 2, correct. So this will form, 1 is 1 by 2 minus 1 by 4. What will be total? R square by 4. Okay. So ultimately I will be getting V average equal to R square is cancelling out, Vz max by 2. So it means that average velocity in case of a fully developed pipe flow is nothing but 50% of the maximum velocity. Okay. Now one question to you, you have to do it by your own. So there is one configuration which is having 2 cylinders. Okay, and fluid is actually in between the 2 cylinders, annular gap between the 2 cylinders. Say first cylinder is having radius r1, second cylinder is having radius r2. Let us consider outer cylinder is moving with velocity omega, inner cylinder is at rest, it is fixed. Okay, and parallel to normal to the board there is z direction. And what we will be considering? We will be considering that because of this rotation, flow is purely in the r and theta plane. In z direction there is no flow. You have to determine this velocity profile, what I have drawn over here. Clear? So this is a question for you. You people have to do it. I will not give the solution of this. So one hint I can give you, you have to take over here the planar symmetry situation, that in z direction there is no variation. So you have to solve the system of equations in only r theta plane. Okay? Is this point clear? Okay, now we will stop, and in addition to this, you have some project component also in your evaluation. Okay, so what you have to do, let me tell you.